Well, hello. Today we are going to be dealing with the seventh central exercise of Theoretical Physics 1, and it's about particles in exponential potential. And it's given as u of x equals u null times the absolute value of x over a to the power n. And let's also write down u null is bigger than 0 and a is bigger than 0. And because of the absolute value, the whole function is going to be positive. So we are only dealing with positive potentials. And the question is, what is our period according to n and e? So in order to interpret it, so we better off be looking at the function. So let's draw it to have a visualization. So for n equals 1, it's going to be a linear function on the positive side and also a linear function, positive function on the negative side. Maybe I should have drawn it better because they are symmetric. So maybe like this. Yeah. And this is x and u of x. For n equals 2, it's a quadratic function. So something like this, maybe. U of x and x. And for n getting bigger and bigger, all it does is going to flatten around 0. So the function is going to flatten around 0. So maybe like this. And then something like this maybe. Yeah, flatter. So, and by infinity, for n equal positive infinity, and let me write it down. It's going to be something like a box. So it's gonna have some border lines which it can't cross, but we're going to look at those later. So let's turn back to our potential and interpret from this interpretation that we have done. Let's go around. And maybe we should also write down what u null and a in a function means. So a given function, let's say this is not equal n, but equal to, but it's a function of u of x, any given function. We can define this function by picking a u null and a corresponding point a, where the a for x equals a, it should be equal u null because a divided by a 1 over n is 1, and u null is going to be u null. U of x is going to be u null. So I can define any function, any u of x, by picking a u null and a corresponding a, or picking a point a and a corresponding point u null. So that's all the function tells us, and it's pretty useful. So let's head back. As I told you before, this is for a non-blocked, non-restricted, non-restricted potential. So there is not a maximum energy level given. So what if an energy level is given? What if here is E and we can't cross the C because it's our maximum energy level? So according to this, I can calculate the potential. So yeah, let's get started with that. So then E is going to be equal the kinetic energy plus our potential energy at a point. So we know that the kinetic energy is mass divided by 2 times the velocity squared. And the velocity I can write down as the derivative of x in respect to t. And let me write it down here. So the kinetic energy is going to be equal m½ times dx divided by dt squared. And we can write this formula down as e minus u of x equals, I'm just going to plug this part in, m½ m½ times dx divided by dt squared. So I can multiply with 2 divided by m. 2 divided by m. Yeah. And it's going to be 2 times e minus u of x divided by m equals dx squared divided by dt squared. Maybe better off just leaving it as it was, dt squared. So I can take the square root of both sides, and it's going to be square root of 2 times e minus u of x divided by m equals dx dt. So this is our velocity. But we were looking for our period. So let's do the integration. But first of all, of course, dt is then going to be equal square root of m divided by 2 times e minus u of x dx. So let's stop at this point, and actually let's integrate first. But yeah, dt is going to be equal the integral of square root of m to e minus u of x dx. Yeah. So let's start, be smart at this point and write down our intervals so that we can calculate our period. So let's think about it. Let's go ahead back here. So our period is going to be, if I start from here, a given point minus x1, and because of symmetry, this point is also going to be x1. No, the negatives, yeah. So if I start from here and head all the way here, it's going to be half of my period. Imagine thinking as like this, a sine function maybe. It's going to be half of our period. So if I start from minus t1 over here, or let's say 0 would be off better. Let's say if I'm starting from 0 and it takes t1 time, from minus x1 to x1, it's going to be equal the period divided by 2, because I also need to come back for calculating the period. So let's remember again. If I go from here to here, it's going to half of my period, and if I go back, it's going to be my full period. So let's write it down. Then t is equal to 2 times the integral from minus x1 to x1, the square root of m divided by 2 times e minus u of x dx. And m is not depending on x, so is the square root of 2. So I can just plug square root of m and divide by square root of 2 out. So let me write it down. Then t is going to be equals 2 times square root of m divided by 2. And the integral of 1 divided by square root of 2, no 2 this time, I plugged it out, e minus u of x dx from minus x1 to x1. Yeah, cool. The other thing that we can do that we know because of symmetry from minus x1 to 0 and 0 to x1 is going to be the same integral. Let's look at the end. So the integration we all know. This part is going to be equal to this part. I know my drawing is bad, but you got it. It's symmetric to the y-axis, so from minus x1 to 0 and 0 to x1 is going to be equal. So we can write it down as 2 times this integral. We can write down as 2 times the integral from 0 to x1 and 1 divided by square root of e minus u of x dx. So, good. So we are only dealing with positive x integers now, x variables. So let me write down t again in this shape form. 2 times, actually let me write down as 2m square root 2m divided by nothing. Why did I do that? So let me write down square root of 2m times 2 and the integral 0 to x1 1 divided by square root of e minus u of x times dx. Yeah, cool, but we still can't integrate this so well, so let's plug u of x in. Let's plug it in and have only x-dependent integral and not u of x. So t was equal then. Let me also write this 2 inside of the root, and it's going to be t equal 8m square root of 8m times the integral from 0 to x1 1 over square root of e, and let's remember what our potential was. Let me actually do this. Yeah, u of x equals u null, so minus u null times the absolute value. Actually, let me just throw the absolute value away because we are only dealing with positive x's, and because of u null and because of a being positive, I can just write down as u null times x divided by a to the power n. Yeah, dx. So perfect, but it still doesn't seem so helpful. So let's try something, and let's try plugging a square root of e out. So we have 1 divided by square root 1 minus something. Maybe thereof we can do something. So let's plug off 1 divided square root of e outside, and therefore it's going to be t equals 8m square root of 8m divided by e times the integral from 0 to x1 1 divided by now 1 minus, and because of non-existing e here, we have to divide it by e. So 1 minus u null divided by e times x to the power n divided by a to the power n. So yeah, and dx, of course not forgetting. So it doesn't seem so helpful at all. What are we going to do with this? Well, at this point, our friend from analysis 1, substitution, is going to help us a lot. So we want to integrate this, and we have a borderline x1. So what if I write down x as a, a variable which is also proportional to x1? So basically, let's say x equals x1 times y. I can do this, why not? So therefore, y is going to be equal x divided by x1, and therefore dy is going derivative of y in respect to x is going to be equal 1 over x1. And from that, I can say dx is equal dy times x1. So yeah, let's plug this in. Let's plug this over here and this nice thingy over here. So from that, we can say t is equal square root of 8m divided by e times the integral from 0 and of course not forgetting the change of the border x1. So y, according to y, it's going to be 1. And so yeah, 1 divided by square root of 1 minus u null divided by e times, yes, now plugging x back in, x1 times y over n divided by a over n dy times x1, not forgetting x1. And because of x1 not depending on y and being a constant here, as I drawn before, a given point, we can plug this x1 out of the integral. So then t is equal square root of 8m divided by e times x1 times the integral from 0 to 1, 1 divided by 1 minus square root of 1 minus u null divided by e times x1 to the power n, x1 to the power n times y to the power n divided by a to the power n, all in the square root dy. So yeah, now our border is from 0 to 1, and we still have an integral we can't solve. So yeah, cool. So let's head back again, and think about it. So we have a given energy level, and we have a maximum energy, which is at the point x1. So I can write down the energy u of x, the potential energy I have in point x1, is going to be equal E. And we know from here that our u of x1 is going to be equal u null times the absolute value of x over a to the power n should be equal E. x1, sorry. Yeah, now from this, I can calculate a value for my x1. So cool, depending on n, of course, but yeah, let's see. So the absolute value, and because of x1 being positive, I can just throw the absolute value away, x1 and a being positive. So x1 divided by a over n is going to be equal then E divided by u null. And if I took the nth root, or maybe you want to like down as this, so the nth root, it's going to be equal x divided by a is going to be equal the nth root, so e divided by u null the power 1 over n. And if I multiply both sides with a, x1 is going to be equal e divided by u null to the power 1 over n times a. Perfect. Perfect. So I can now take this nice definition of x1 and plug it in back over here, the last integration we found. So over here. So let's plug it in and see what happens. So then, and also I can also plug it in here. So it's perfect. Sorry for that. So t is going to be equal to square root of 8m divided by e times, what was our x? 1. Let's look at it again. Times e divided by u null to the power 1 over n times a times the integral from 0 to 1 divided by square root of 1 minus u null divided by e times the power of x1 over n. So let's do that here. Therefore, I can say x1 over n is going to be equal a over n times, and of course, just multiplying n with 1 over n, it's going to be e divided by u null. So let's plug it in down here, times a over n times e divided by u null times y over n divided by a over n. And look at this. U null, e, a over n, a to the power n, a to the power n. Perfect, and also not forgetting dy. Perfection. So now I can write down t as square root of 8m divided by e times e divided by u null to the power 1 over n times a, and the integral from 0 to 1 divided by square root of 1 minus y to the n dy. And this is pretty much what we were looking for. But we can still solve this integral with our knowledge, and it's also not given in the paper. So let me write it down as, first and foremost, write down as it's in the paper. So this t is also depending on n. So then t in n of e, I'm just going to plug this 8 out now as 2 times square root of 2. So it's going to be square root of 2m divided by e times e divided by u null to the power 1 over n times a times 2 integrated 0 to 1 divided by square root of 1 minus y over n dy. And by looking at this, I see this as a constant. I see this as a constant, which is depending on n, because of this over here, and so I can define it as an and give its values depending on n. So let's write it down again as it's in the paper. So Tn of e is going to be equal to square root of 2m divided by e times e divided by u null to the power 1 over n times a over n, and this was what we were looking for from the beginning. So I asked myself, maybe you're also asking also yourself, so how do we do this integration? This part, the right part, the an. So basically, this integration has something to do with gamma functions. So maybe you want to remember gamma function is of z is equal 0 to infinity t over z minus 1 times e over minus t dt. So a bit complicated, this integral is. So let me just write down. Then it's an is going to be equal 2 times square root of pi times the gamma function of 1 plus 1 over n divided by the gamma function of 1/2 plus 1 over n. And in the paper, there are also some values given for n equals 1, 2, 3, 4, and infinite. So let me write them down. N an 1, 2, 3, 4, infinite. And for 1 it's 4, 2 it's pi, for 3 is 2.0, yeah, 4, 2, and for infinite 2, yeah. So I'll be drawing and calculating these with you, and these is not so relevant right now, but these are also extremely, and also I'm going to draw this and then interpret it, but these two is not relevant for now, and it's also not it's not given in the paper, the explanation and some other stuff, but these are also extremely relevant for quantum mechanics, and this topic itself is actually extremely relevant with quantum mechanics and wave functions, so I highly recommend you to check it out. But these two is extremely important with quantum mechanics, with something like Schrödinger's equation, etc. But today it's not relevant for us, and I'll be interpreting only these three. So let me write it down. Then for t1 of e is going to be equal square root of 2m divided by e, if I'm not remembering wrong, yeah, times e divided by u null. I plugged 1 in, and 1 over 1 is going to be 1, times a, times, and an was 4. So this is going to be equal square root of 2m times e divided by u null. U null is not in the square root, and times a, times 4a. Cool. So let me draw this. So this is the period for n equals 1, and as you can see, this is triangular, so it's also known as triangular potential. Smart. Well, yeah, so let's do it for n equals 2, as it's also done in the 8th exercise, I think. So you might also check it out. So t2 of e is going to be equal square root of 2m divided by e times e over u null to the power 1 over 2, so it's square rooted, times a times, and for 2, an is going to be pi. And something's going to come out that we saw before. Maybe I should have given also an example for this triangular potential. So maybe m times g times x. Why not? If I'm going higher on the plane, I'm going to get more potential, and it's going to be triangular because of x, the exponent of x being 1. So an example could be that. So let's head back. As I told, an was pi, and because of that, square root of 2m divided by u null. U null is now in the square root times a times pi. So seems pretty interesting to me because this is the only n value that our period is independent from our total energy. So it doesn't matter what energy you have. So the period is going to be the same for all maximum energy levels. Yeah. And this we know as harmonic oscillation, harmonische Oszillator. And we also dealt with it in the first semester, and it's extremely relevant. So for n equals infinite, I'll also do it. For t infinite of e is going to be then square root of 2m divided by e times e divided by u null to the power 1 over infinite times a times, and am was 2. So let's look at this a bit. So here we know from analysis 1, this is going to be 1 because the infinite root of something is going to be 1. Not everything, but in this case, for the energy level being not equal to 0. And yeah, so therefore, this is going to be equal square root of 2m divided by e times a times 2. And we can tell, as I drawn it in the first hand, this looks something like this. And I also should have drawn for the 2, n equals 2. It's going to be something like this. And an example for that, as I already told you, would be harmonic oscillation, and it's 1/2 kx squared. So you can see this is x squared now here. So and for an example of this potential, we can give the potential well, which is extremely relevant in quantum mechanics, quantum physics overall. And in German, it's Potenzpotential. I'm pretty sure you have already heard in some sort of way or form. And yeah, let's show that this is actually true. So, hey, sorry for the inconvenience, had some technical issues. So let's head straight back. As I was telling, let's prove that t infinite being equal to square root of 2m divided by e times 2a being true. So let me write down also here x and here u of x. And let's look at this region that we're going to be calculating our period, this border line inside these borders. Here in this region, u of x is going to be 0. So we have energy, if we have, but it's not in form of potential energy. So let's look at this. So u of x is going to be equal to u null times, in this case, let me write infinite, times the absolute value of x over a over infinite. Maybe it's not that right to just write down infinite. Maybe I should have better off write it as limit, but let's go this way. So for this being equal to 0, this part should be 0 because it's the equation being 0 is independent from u null, so it should be depending on x over a. So for this being 0, x divided by a, the absolute value of x divided by a, should be smaller than 1 because we're having the exponent infinite. So for that, we can say, x should be smaller than a and bigger than minus a. Simple mathematics. So yeah, now we know our borderlines. So this point here is going to be minus a, and this point here is going to be a. So cool. Let's head back and remember what actually the period was. The period was my time that I take from going from this point to this point and heading back. So in this case, I have a velocity, a kinetic energy, and it's going to be v. Let's say it's v. And the total road I take from minus a to a and heading back is going to be, this is a, this here is a, this here is also a, so it's going to be delta S equals 4a. So we know from the definition of our period that t infinite is going to be equal to 4a divided by v. So cool, yeah. In one hand, we have now this, and in other hand, we have this. Doesn't seem so connected to each other. Well, let's prove this and end this exercise. So, as we know, potential energy is going to be in this region, 0, in this region, 0. So then the total energy will be depending on our kinetic energy. So E is going to be kinetic energy, and therefore E is going to be m½ v squared. So therefore, we can form this down as v squared equals 2e divided by m, and v is going to be then square root of 2e divided by m. Let's plug this in. So t is going to be, t infinite is going to be 4a divided by square root of 2e divided by m, and this should be equal to 2a times and square root of 2m divided by e. Let's multiply both sides with square root of 2e divided by m. So therefore, t infinite is going to be 4a is going to be 2a times square root of 2m divided by e times square root of 2e divided by m, and we can shorten these out, and square root of 2 times square root of 2 is going to be 2, and therefore 4a equals 4a. And this is a proof that our equation is true. And yeah, I think that's all. Maybe another point I could say that 4a is going to be our distance that we cross. I already mentioned it before, but no harm at mentioning it again. So this going here and going back is going to be 4a, and this is known as in German the Laufstrecke in our OL. So yeah, this was all of it. Thank you. Maybe for a quick recap, you should notice that t for an exponential potential of u of x being equal to u null times the absolute value of x over a to the power n has a period of this. So Tn of depending on e and n is going to be equal square root of 2m divided by e times e divided by u null to the power of 1 over n times a times an, whereas an is going to be equal to times 0 to 1, the integral from 0 to 1 of 1 divided by square root of 1 minus y to the power n dy. And that has something to do with gamma functions. And the period for T2, n equals 2, is independent from the energy level. And you should also see that in the 8th exercise. So I recommend you to check it out. And thank you, and I wish you a nice day.